Hello, everyone. My name is Nikita Joshi, and today I'll present our paper titled An Instrumented Office Chair with a Steerable Projector for Personal Spatial Augmented Reality. This work was done in collaboration with Anthony, Jeremy, and Dan at the University of Waterloo. In this work, we contribute the idea of using an office chair as a standalone input and output device for personal and portable spatial augmented reality. This could be used in a wide variety of scenarios, like, for example, to show a "be back soon" message when you're away from your desk, or to enhance physical drawing surfaces like a whiteboard. Spatial augmented reality, SAR for short, is a type of augmented reality that uses projection mapping to place content on existing surfaces in the environment. Unlike augmented reality that is shown to users through a head-mounted display, spatial augmented reality can enable more ad hoc and peripheral displays that are triggered by both implicit and explicit interactions performed by the user in the environment. Often, SAR setups consist of environment-mounted projectors and depth cameras, which can enable a wide range and coverage of a room. They are usually quite difficult to set up and move between rooms. So some examples include multi-projector setups that are enabled by systems like Room Alive, and steerable projectors like Beamatron. Self-contained SAR experiences are often much more portable, allowing for SAR to be used in a wider range of environments. However, they are usually on a much smaller scale and are geared towards personal use. Some examples include handheld projectors and projectors that are worn, but these can be cumbersome to use or may not be socially acceptable. Other examples include projectors that are integrated into smaller objects, but these usually can appear bulky and have limited range. When SAR capabilities are integrated into larger objects like pieces of furniture, SAR can remain relatively portable while still providing enough room for larger hardware that is necessary for SAR and to give an adequate range. And while prior work has explored, for example, integrating SAR into things like lamps, one object that really stands out to us are chairs. And this is because they're ubiquitous, they're easy to move between rooms, yet they're still large enough to support all of the necessary equipment. And work by SI and colleagues explored the idea of using a steerable projector to augment a wheelchair, which allows wheelchair users to perform pointing tasks through an extendable arm that's projected in the environment. So we build on all of this prior work to contribute the idea of using an office chair for personal SAR, which effectively turns an office chair into a portable and ubiquitous computing device. To explore the concept of chair-enabled SAR, we created a proof of concept chair. We attach a steerable projector and depth camera to the side of a standard office chair and instrumented with a variety of sensors to track the seated posture, tilt, touch input, and its position within the room. Based on prior work, our goal is to create a SAR system that focuses on personal and peripheral use, that is context aware, and that considers input and output holistically. Office chairs are compelling to use, as prior work suggests that office chairs can be used for both implicit and explicit input. So for example, the implicit interaction of rotating may indicate shifting focus, which is leveraged by a chair mouse to automatically move a cursor across multi-monitor setups. But bouncing is much more explicit, which Probst and colleagues leverage as a way to perform peripheral interactions on a computer while seated, so like undoing and redoing operations. So we aim to leverage these implicit and explicit inputs as a way to integrate with portable and personal SAR, which would allow the office chair to become a standalone input and output device. So I'll now describe the different components of our prototype system. So as I just mentioned, to render content onto surfaces in the environment, we use a Pico projector, which is attached to a servo-actuated pan tilt mount. It's placed along the side of the chair, just underneath the right armrest. And this position allows the projector to rotate to place content in front of, above, below, and to the right of the chair. In roughly the same location, we attach a depth camera. The camera is connected to a Raspberry Pi, and the color and depth images are streamed to a Unity application running on a main computer. The images are used to estimate the position and rotation of the chair using SLAM, to generate a 3D mesh of the environment, and this mesh kind of serves as a base that can be customized with SAR in Unity. To estimate the seated posture, FSRs are placed along the seat and back and two armrests to track implicit chair interactions. And this approach has been done in prior work. We also attach an IMU to the back of the chair to track its tilt. For explicit touch input, bands of copper tape are placed along the edges of the armrests, and this allows users to tap and swipe this area for input. All the sensors are connected to an Arduino that's placed underneath the chair, and all of this data is streamed to the main computer through the Raspberry Pi. In Unity, the seated posture and touch input can be visualized for debugging purposes, and it can all be integrated into SAR applications that the user wants to create. So as alluded to throughout, we use Unity to create a software toolkit for users to use and to unify all the different components of the chair that we created. And this toolkit has three primary goals, and a user's typical workflow inside of Unity would resemble the following. So first, they would generate a 3D mesh of the room by moving the chair around a new space. Second, using the generated mesh from this calibration phase, the user would create visual displays for the projector to display by dragging and dropping assets onto different surfaces in the scene. And this could be anything that they want to display. Lastly, they would map different implicit and explicit chair inputs to environment interactions to suit the different application scenarios, which would allow the user to control when the display will become visible, how menus will be selected, and when it will disappear, and more. Using the proof of concept chair, we created 11 different applications to show the potential for chair-enabled SAR. The applications are grouped into 3 categories for narration purposes. These include showing different types of notifications, enhancing work-related tasks, and encouraging work breaks and relaxation. To be short, I will only discuss a few of them in this presentation, so I encourage you to see the paper for more details. So first, we have a notification that's shown on a nearby door. Swiping the armrest will show different types of notifications, and applying pressure will show a brief description of the contents. To see a more detailed view, the user can swivel the chair to face a nearby wall, and this view can be dismissed subtly by crossing their legs. When working with tools or circuitry, when the chair is placed near a workbench, a video tutorial is displayed beside them. And this tutorial can be paused and played by applying pressure on the armrests. When the chair is then turned to face a set of drawers, the projector will rotate to display a list of inventory on the front. When the user leans far back while seated, which may suggest taking a moment to pause or relax, the projector rotates to display a deep breathing exercise on the ceiling that the user can follow along with while they're leaning far back and looking up. Using the different applications, we conducted a survey to better understand ideal use cases for chair-enabled SAR. Respondents were asked to watch videos of all of the demos and answer a series of Likert questions about their understanding, perceived usefulness, and social comfort. We also asked participants about their current behaviors with chairs, and we report the central tendencies based on 41 responses. Overall, the results show that many chair behaviors are common, making them much more likely to be associated with implicit input. However, some behaviors, like tilting the seat back while standing, are much less common, making them more likely to be associated with explicit input. Overall, all of the applications were well understood and were generally perceived to be comfortable, but usefulness was less decisive. Working with tools and reducing eye strain were perceived as useful and comfortable by a majority of the respondents, and deep breathing exercises were also considered to be useful and comfortable. However, displaying detailed notifications through a notification tray was perceived to be less useful and less comfortable, but more ambient forms of notifications were much more useful and comfortable. We dive into the free-form responses to give some insights into ways in which chair-enabled SAR can be improved. And one major concern for participants was privacy. And we proposed using some chair inputs to help preserve privacy, like crossing your legs to dismiss a notification. But relying solely on chair input for privacy is inadequate. So these should be combined with other visualization techniques like modifying the the display's level of abstraction in public environments. There's also a conflict between some of the input mappings. So for example, with the deep breathing exercises, although it's very easy to learn that leaning back means viewing a deep breathing exercise, it may also draw some unwanted attention and actually impact the privacy of the interaction itself. So multiple options, including those that are much more discrete, should be provided to suit the context of use. When interactions for dismissing content are tied to maintaining specific poses, like leaning forward, this can be physically uncomfortable, especially for longer tasks like viewing a slideshow during a meeting. So having different sets of interactions for displaying, maintaining, and dismissing the content could all help resolve these concerns. There's also the risk of conflicting interaction, like causing unintended input. And visualization techniques, like visualizing feed forward, could be integrated into our system to reduce the chances of accidental input. Overall, we contribute the idea of using a chair for a chair-enabled SAR and explore it through a proof of concept prototype, a collection of demos, and results from a survey. Our work provides yet another solution for creating a more portable SAR that is easy to deploy and integrate into everyday life. Thank you so much, and I'm happy to answer questions.